Thank you. Sir, are you telling anything? I couldn't hear you.
No, we can. I think we can start the
Yes.
streaming.
Yes, sir.
Now it's 6:05.
She has started, I think. Rama has started that streaming.
No, recording also we can start.
Recording also we can start. Yes, sir.
No, 6058.
Yes. Akila, could you start that recording? Akila, Rama.
Started recording, sir.
Okay, we'll start now. In the interest of time, we'll start. Greetings and good evening to one and all. On behalf of the organizing units, Computer Society of India, Chennai chapter, IEEE Computer Society, Madras, ACM Chennai, I extend a warm welcome to our esteemed speaker, Mr. Kiran Vijayakumar, members and my colleagues from the organizing units, and all the participants who have joined the Google Meet and others watching the YouTube streaming of today's presentation on striving for simplicity in software development. When we all started the career in computing, at least myself and few seniors who are present here, the software meant either systems and utility software or application software. The software component in a computing solution was about 10 to 15%, and the leasing companies used to refuse for funding the software. The applications were developed using programming languages, and the data management was through file systems. There were no databases or programming environment. The software engineering as a discipline was not there. From that level, the ecosystem for software development has been evolving at a rapid pace with more significance in the last decade. However, these developments have not made the job of an average developer any easier. The variety of programming languages, frameworks, libraries, devices to be supported, platforms, and AI tools can confound even the best when it comes to starting a project fresh. Today's presentation will look at the underlying philosophy behind some of these components that have stood the test of time in the world of software, adapting some of the design principles used there, and being cognizant of the complexities in the current landscape could help developers help in building the high quality software without sacrificing the element of simplicity. With this brief note on the today's topic, now it is my pleasure to formally introduce our presenter, Mr. Kiran Vijayakumar. Mr. Kiran has over 25 years of experience in software development in various roles. He is currently working as the head of product engineering at matrimony.com, India's largest vet tech company, serving more than 5 million customers. In his earlier roles, he has led engineering projects across several industry segments such as retail, telecom, enterprise, computing, education, and gaming. With this brief intro to the subject of our today's presentation and the speaker, may I request Mr. Kiran to enlighten the participants on simplifying software development process. Over to Mr. Kiran, please.
Thank you, sir, for the kind words. Let me share my screen first. Are you able to see the screen?
Yes,
Yes, sir. Yes,
Okay,
yes.
thank you. Sure. So as Mohan sir said, when I started my career in the 90s, software development seemed very simple. There was just one programming language that I had to know, and that is C. And most of my college life, I had written programs in C. And during my initial years of career also, I continued to do C programming. And I think I was above average, at least I have very happy memories about it. But as my career progressed, I had to learn a lot more technologies, more programming languages, right? The way applications function, etc. And looking back over 25 years, almost every 2-3 years, it has been a new leap or new discovery, right? And it is just getting more complex. There are still systems which are developed fully in C. For example, one of the most popular operating systems, Linux, is written in C, right? And to think back to my college days and comparing it with the student who is currently learning computer science or another engineering stream, I feel it is a really unenvious task, right? And when someone young is looking for a career opportunity, they'll be confused. Okay, what am I supposed to learn? And even for someone who has found a job and is starting on his or her career, there are a lot more things to learn and explore. So in today's topic, I would like to focus on most of the non-tech aspects. I'm sure that CSI has been doing a lot of in-depth technology-related talks, etc. So considering that this is something which is not taught in students, and most of us have to find it or learn it the hard way through experience, right? It's literally baptism by fire. And more importantly, it's Friday evening, almost the end of a busy week. I'll try to keep this as simple as possible, right? So in the next 45 to 50 minutes, let me give some of my perspectives on what software development should be. Right? And at the end of this, we'll take the questions also. I've got a bunch of questions already from people who have registered for the talk, so we'll go through that also. So if you have any questions while going through this talk, please keep the questions with you and we'll take them at the end. So let me start with a story, right? On right, you can right on the screen, you can see a map of Denmark, and specifically a town called Billund, which has a population of 6,600 people. Now, this is a company headquartered here and is the world's largest manufacturer of tires. It was founded by a person named Ole Kirk Christiansen, and its name comes from Danish for play well. And it's a company that we all know. If any of you know the name of the company, please feel free to type it as a chat message, right? And sure, you would have seen it in multiple places. Some of you may have used it as well. It is a company called Lego, right? And it's extremely popular across the world. Now, how did they become such a global phenomenon? The company started in 1930s as a traditional toy maker, right? And they built products just like the other toy makers. But in 1940s, they decided to focus on developing a cohesive system where a set of toys were interrelated. And they came up with this concept of interlocking bricks. Bricks is a term which they use to technically describe or name the pieces which make up a Lego system. So Ole, the founder's son, his name is Gottfried, he identified 6 features which he called the company's principles of play. And these principles were issued to every Lego employee. Right? And what were these principles of play? They're fairly straightforward. The first was stated limited in size without setting limitations for imagination. Second, affordable. The third, simple, durable, and offer rich variations. Fourth, for girls, for boys, fun for every age. Fifth, a classic among toys without need of renewal. Sixth, easy to distribute. So the first one, limited in size without setting limitations. It can be as simple as a 3-piece animal, a 4-piece, etc., to something more complex. Right? On the left, you can see a Bugatti car in real life, and on the right is a replica of that made using Lego blocks, right? Matching size for size, part for part, extra. So that's what Gottfried meant by without setting limitations for imagination. Now, can you guess which of these Bugattis is drivable? The left one, of course, is drivable. And some of you may have guessed the answer rightly. In fact, both of them are drivable. So it's an incredible system that Lego built without setting limitations for imagination. The second point said single, durable, and offer rich variations. So there are basic brick shapes like 1 into 1, 2 into 2, 1 into 2, 2 into 2, etc. Right? These are essentially how many pins are there to interlock with another piece. These were made from a material called ABS plastic, which made them durable, which is also non-toxic, considering that people of all ages were using them. Less prone to discoloration and warping meaning bending, etc. And they were resistant to heat, acids, chemicals, etc. So just 6 2 into 4 bricks can be combined in almost a billion ways. So that is what he meant by rich variations. And this was a classic among toys without the need of renewal. So every year you don't need to buy a new one. Standard set, which they call as a stud and tube coupling system, it can be operated the hands of any size, essentially. And when they are attached to each other, it created instant stability, which was called as clutch power by Lego. And it was also backward compatible. It's a term which we commonly use and hear in software engineering as well, right? It meant that a new brick, which is released in, say, 2023, can still work with a set which was made 50 years back, or most probably even one of the earliest sets. Now let me move on to another story. Something closer home, more technical. So sometime in the 1960s, Bell Labs, right, the world famous organization, was at a crossroad. In the late 1960s, Bell Labs, Massachusetts Institute of Technology, and General Electric, they were all giants in their fields at that time in the US. They were together developing a time-sharing system called Multics, allowing multiple users to access a mainframe system simultaneously. Right? Remember, this was the early days of computing. And the project was moving very slow. So very dissatisfied with project's progress, Bell Labs management withdrew from this partnership. Now, around the same time, an employee at the Bell Labs, specifically in 1969, he was working on a disk scheduling algorithm that would try to maximize throughput on any disk. But this is particularly for a PDP-7 system, very tall single platter disk drive. So here you can see a PDP-7 system. Yeah, for the younger generation, this may look very ancient. It may look like a kitchen utensil, appliance, or something very industrial, right? But this is an early computer. The most powerful in those days, called the PDP-7. And Ken Thompson was building an algorithm for scheduling on this. Now, while testing the algorithm, he realized that he was just 3 weeks from making an operating system. And around that same time, his wife had taken off to visit his parents in California, taking their son along. So he broke down his work into 3 units: an editor, an assembler, and a kernel. And he wrote each of these in the next 3 weeks, right, undisturbed. Thus began the life of Unix. The name was chosen as a pun on Multics, which was the earlier project that all MIT, Bell Labs, and General Electric were trying to collaborate on. Now, Unix became extremely popular in the ensuing decades, and it even inspired the perhaps the most popular operating system today, Linux. They share a lot of fundamental design philosophies, engineering philosophies, right? And it is well known by the term Unix philosophy. So what it essentially means is that the Unix philosophy covers a set of cultural norms and philosophical approaches to minimalist modular software development. And this was based on the experience of the leading developers of the Unix operating system, like Douglas McElroy, Ken Thompson, Dennis Ritchie, etc. Right? And this philosophy emphasized building simple, short, clear, modular, and extensible code that could be easily maintained and reused by developers other than its creators. One of those early giants, Doug McElroy, wrote about this in the Bell System Technical Journal in 1978. So this is verbatim taken from that. One of the first philosophical tenets was make each program do one thing well. To do a new job, build afresh rather than complicate old programs by adding new features. Expect the output of every program to become the input to another as yet unknown program. Don't clutter output with extraneous information. Avoid stringently columnar or binary input formats. Don't insist on interactive input. Design and build software, even operating systems, to be tried early, ideally within weeks. Don't hesitate to throw away the clumsy parts and rebuild them. And the fourth one, use tools in preference to unskilled help to lighten a programming task, even if you have to detour to build the tools and expect to throw some of them out after you have finished them. A very good example of the Unix philosophy was the pipe implementation. People who are working on Mac OS or Linux or FreeBSD or even Windows would be familiar with the concept of pipes. Right? To illustrate this, let's look at an example. Imagine that we have a very high traffic web server which is serving images with logs in the following format. So what you see here is a single line of log when it is created when a user accesses a file. In this case, I have chosen a file name called thebestmeme.jpg, right? And some user from this IP address has accessed this image at this timestamp, that's yesterday, midnight. And this was referenced from reddit.com using this browser. All these are color-coded differently to indicate that, okay, these are unique pieces of information which make up the log file, right? And this entire string is the identifier for the browser. In technical terms, the user agent header which comes, right? Now, if the high traffic web server, say, serves 100 million images per day, and someone asks you to find the image which was used by users the maximum number of times yesterday, there are many ways you can achieve this, right? In fact, millions of ways in which you can do it. But one of the ways, using the Unix philosophy, to use pipes to do this. So here you use a series of commands separated by the pipe symbol and achieve the output. So let's try to split this, the entire sequence of commands, which is just one line, to get the final answer, right? It says this particular file, catdogfriends.jpg, was served about 19 million times out of the 100 million. Now, this entire command chain is made up of 1, 2, 3, 4, and 5 different commands. Now, cat is one of the simplest Unix utilities available. It just concatenates a file onto the standard output. So if I just say cat this file name, this entire file name, it'll just print the entire file to the terminal. That's it. It does nothing more than that. And that output is piped to the second command, which is a cut command. Here, cut takes some parameters. So cut essentially says, whatever input is coming, I need that input, each line to be delimited by a space, which means if there are spaces in that line, separate it out as different fields and give me the 7th field out of those. Right? That is what this indicates. So here you have multiple fields. The first one was an IP address. Then there are 2 fields which were hyphen. The 4th was the timestamp. 5th also was the time zone. 6th was the HTTP method. 7th is the actual file name or the image name. So at the end of the first command execution, you get 100 million lines onto the screen printed, and that pipe to the cut command means that there will be 100 million lines, but only the file name, the image name alone will be printed. The rest of the things are omitted. The third is the sort command. Right? So essentially sort the entire output in alphabetical order. And that is piped to a program called unique, which takes any input and then finds what are the unique occurrences in that input. So out of the 100 million, there will be multiple files which are accessed multiple times. And -c of unique command gives you the count pertaining to each of those. Right? And this will not be in any sorted order. Now, if we want to find out the topmost, we have to again sort it. So here what we are saying is sort, but consider the input as a number, because the unique -c prints it in this format. You have the count followed by the file name. And since we want it in the descending order, we also knew R, which is to do a reverse sort. So at the end of the sort -nr, you have the list of all the unique files with the count. But we are interested only in a single file, which was used by the maximum number of users. Right? For that, we want to just get one line out of the entire output. That is achieved by head. So if you look at it, if you had to write this in a C program or a Java program, or JavaScript, or TypeScript, or Python, it would have taken probably at minimum 5 lines of code, right? And all this could be achieved by writing a single line on the command line, Unix or Linux command line, right? So this encapsulates the Unix philosophy in a very good way. So here, each of these commands had one job to do, right? And they did it perfectly. And they could also communicate with each other. So just going back to what Doug McIlroy had to say about the Unix philosophy, right? All these were achieved. And it was not just in Unix. People continued to use these in many other fields as well. Right? So in system design, in embedded design, in web applications, etc., these principles are being used in a big way. Now let's move on to something which is slightly non-technical. So this person's name is Dieter Rams, one of the most famous industrial designers in the world, born in Germany. And the products that you see here were all designed by him. And they have inspired millions of products, including the Apple iPhone, iPod, the Mac, etc. Right? And he had a set of principles which he called as a good design principles. So in his view, good design is innovative, makes a product useful, is aesthetic, makes a product understandable, is unobtrusive, honest, long-lasting, thorough down to the last detail, is environmentally friendly, and is as little design as possible. Now, these 3 stories that I mentioned, the first being Lego, the second about the Unix philosophy, and the third about the principles by Dieter Rams. They have a lot of similarities if you think about it fundamentally, right? I don't want to crystallize that into just a few points, but think about each of these things. What is it that made them all popular, long-lasting? And you will find that all those are applications or philosophies which you can use in your day-to-day activities while doing software engineering tasks. Now, some of those principles, right, which I consider as good for software development, I've tried to cover in the following slides. So let's go through them also quickly. The first is to divide and conquer. And more often than not, you are going to find problems which are hard to solve. Right? And these are hard to solve primarily due to their complexity. If you ask people who have spent a lot of time designing and building systems, the first advice you will get from them would be to break the problem into smaller problems. Once you break the bigger problem into sub-problems, then it is easier to divide. It's easier to conquer, essentially, right? The smaller bite-sized sub-problems will have lesser complexity, and you will be able to solve each of those one at a time. In fact, if you think back to the Unix pipe example, that was also a hard problem, right? If you're not familiar with, say, the Unix system commands, etc., and your familiarity is just with one programming language, you would have to think about a lot of things. You would have to think about sorting algorithms. You would have to think about memory size. You would have to think about disk size, CPU usage, and then come up with a solution. Now, by dividing it into sub-problems, giving each of those sub-problems to a utility or command or tool, which could take care of that sub-problem easily, we were able to achieve all that very quickly. And this is not a skill that can be acquired from textbooks or by theory, right? And this comes only with practice. And as and when you solve more complex problems, you will get better at it. The second principle is increase cohesion. So what is cohesion? Cohesion essentially is grouping things which make sense together. Essentially, organizing your functionality that way it is much more easier to manage and maintain. And this also simplifies the system that you're building. Some examples of this is, say, authentication related or authorization related functionality. Say, math library. For example, in Python, you would find that packages specific to each of the core functionality would have been created as a package, right? Math operations, file operations, or image manipulations. All this would have been done independently, rather than one Python binary which can do everything. Now, Python is just an example that I mentioned, but you can see that the principle of increased cohesion is evident around us in many ways. Look at programming languages, frameworks, platforms, libraries that you use, you will find them in play almost every day. The third is to reduce coupling. So when we are building something, tight coupling occurs when packages, modules, classes, or files are very interdependent. Now, long back when, say, the programming languages were in their infancy, right? Applications would be one tight bundle. where almost all the logic would be together in one executable and you would have to work with that. But now that's not the case. There is a lot more complexity. If you're building a web server, you need to think about what would be your base web server. Then there would be an application layer for the business functionality, right? Then there would be a data layer or multiple data layers like a database or in-memory cache. There could be external APIs that you need to call. For example, if you want to make a payment, you would call a payment gateway API, right? If you want to send an SMS to a customer, you would call an API of an SMS provider. So there are lots of interactions which happen between modules, between packages, right? And by tightly coupling all these things, we are increasing the complexity. Assume that one of the packages has some changes or breaks, then the whole system could be at jeopardy because some of its parts depend on the package that is malfunctioned. So reducing coupling or reducing tight coupling rather, when you're building something, makes it easy for you to debug and fix any component that fails. Abstraction is a concept that we all learn as part of learning programming, right? Especially object-oriented programming gives you a very good view of what abstraction is. And in a nutshell, something that is more abstract is more generalized. To give an example here, a function that takes in a shape and then displays that particular shape on the screen based on the properties is better than something which is implemented specifically for a triangle or a rectangle. Imagine if you have to build one function for each of the polygons, then you're going to write a very large number of functions. But a common function or a generalized function which can take in any shape and take in the arguments or parameters which are required to create that shape would be far easier for someone to look up, understand, implement, debug. So increased abstraction becomes important when building software. It also reduces the number of moving parts and increases security. Increasing reusability. So again, going back to the Unix philosophy, all the commands that you saw could help in writing a very large number of applications. In fact, I mean, very, very complex applications written using just shell script. If I'm not mistaken, one of the early implementations of Google crawlers, right, to build the search index was relied heavily on shell scripts for getting the data from the web pages, storing it, extracting the data, and then indexing it. Of course, it has now become a lot more complex, right? But the power of using these tools can be immense depending on the context and what you want to achieve. So reusability goes sort of hand in hand with abstraction, right? Rather than writing a specific function that does one thing well, but only works in maybe one specific implementation, we can make it general. That is a bit more abstract to allow reusability in different contexts. And this might call for upfront investment of time, and sometimes it's worth making that small sacrifice upfront instead of having to go back, understand the code, rewrite it, and then make another function. Again, this is not an easy skill to build, right? You have to be very clear when to reuse, when not to reuse, etc. The next point is on flexibility. right? You have to agree that your systems are going to change in the future. There will be multiple requirements that will force you to make changes. So currently your system being simple does not mean that it is going to retain that simplicity in the future. You also have to anticipate external headwinds. When I say external headwinds, these are external dependencies that your project or system need to be very careful about. Some of the external headwinds can be API breakages from a third party, feature being obsolete, some of the features being decommissioned, security issues in an external system. We have seen a lot of supply chain attacks in recent times because we depend more on external services these days. Sometimes it could be a regulatory changes, or it could be service unavailability, which could impact your application also. If everything is managed by you, you have a control on external headwinds, but unfortunately, that's not the case. Almost all applications that we build these days have external dependencies, and you have to be prepared for any eventuality with respect to these. Designing for portability. So when designing system, you need to remember that it may be used on a different platform or device than what you're currently targeting. You may start off making a web application just for the web, but then if it becomes popular, you may want to turn it into an iOS app, an Android app, a Windows desktop application, or something like that. And at that point, it'll be very costly and time consuming if you go and change the fundamental design of your web application. So, especially with respect to external facing application of web scale, anticipate for future growth, anticipate for scalability, right? And keeping those design considerations will make it easier for you to make it portable. The web scale or the web application is just an example. It could be portability with respect to a CPU architecture, or it could be even an operating system portability, right? It could be at any level. Design for testability, making sure that whatever you build will not break anything, because your software is going to evolve. In evolutionary biology, there is this principle called the Red Queen phenomenon. So even to stay at the same place, you have to keep running, right? For an Android application, which is in the Play Store, you have to make sure that your application works when the next Android OS upgrade happens, right? There could be functions which are deprecated, which means that you will have to make changes to the code, even though the core functionality is not changing. So while working on large scale systems and large code bases, testability is an extremely important concern. Any change that you make on these systems could break something else, right? These are called regressions. So if you design for testability and invest in automation, then things become a lot simpler. Any change into the complex systems can be immediately validated and tested. Being defensive about your design and development. Right? So we work with audiences of various skill levels, people of various skill levels. When I say people, your colleagues, right, friends, they may have different language proficiency. Right? Here, by language proficiency, I mean English language proficiency, because most of the variable names, the code comments, etc., we write in English. And it is extremely important that you communicate very clearly with your design and code. So work with the assumption that your audience is going to be of an average proficiency and you are communicating very clearly. It also means that you are validating all the inputs which are coming from the user. You're not opening doors of vulnerability. You're also communicating clearly back to the user through good error messages, clean interfaces, etc. These principles go a very long way in making your engineering efforts robust. Now, if you look at the field of architecture, right, or building construction, the building mindset is very similar. A strong foundation enables us to build more and better on top. So some of the key infrastructure like plumbing, wiring, sewage, waste disposal cannot be afterthoughts. So you have to pay a lot of attention to this while building the foundation. Once you have this in place, decor changes, paint, fixtures, expansion become very easy. You can make all these changes frequently without cost overruns or major restructuring, etc. So the principles that good architects use, build good constructors use, they are all applicable to software engineering as well. Now, all these things that I've said so far, nothing is set in stone. I said that you have to, probably apply the Unix philosophy while developing, etc. But then it may not be applicable for something like, say, an embedded system where you have a lot of limitations on CPU and memory, right? So you may build one tool which can serve multiple purposes. But if you're talking about an operating system or a web scale application, then it makes sense to compartmentalize, decompose the problem into multiple layers, and then solve for each of those layers in between, right? So I talked about simplicity and how some of the philosophies that were adopted in Lego, Unix, in the data RAM designs, etc., look very simple and have been popular. But simple doesn't mean that it can be achieved easily. In fact, a lot of hard work goes into making things simple. And software engineering is an art more than a science, right? A lot of people may not agree with this sentiment, but over the years, this is what I've found. And you learn by making mistakes, and you learn by looking at what has worked in the past. There are a lot of projects that you can see and adopt from, principles that you can shamelessly copy from, right? And take help from mentors, etc. So it is important to pay attention to the aspect of simplicity right from an early part of your career, and you can see that you will constantly get better at it. Just by learning a programming language or a particular technology or platform, you're not going to become a great software engineer. It is only by building good products, right, or good software components that you can help others. When I say others, it is not just the users, end users, but others within your ecosystem also. So if I have to crystallize whatever I've covered in my earlier slides, first and foremost, I would say that understanding the context very clearly is the most important thing before making critical design decisions. And once you have a fairly simple architecture and design in front of you, when you have done the composition of the sub-problems, then the development part becomes easy. When you're embarking on this journey, a lot of people try to aim for perfection, but that is a very lofty goal to chase. I don't think that's probably the right goal to chase also. more often than not, completeness will help you more than perfection. Just like I said earlier, right? Nothing is set in stone. So you have to question status quo and ancient wisdom. But then questioning ancient wisdom is not always the right thing also. In fact, many of the problems that you're trying to solve may have already been solved by someone else. So it's always good to explore what has been there in the ecosystem, to read upon literature, right? To look at the best practices which are documented, essentially stand on the shoulder of giants. It is also knowing oneself that helps us go a long way. There's a saying that to a hammer, everything looks like a nail. So rather than be a one-trick pony, explore dichotomies or trichotomies, whatever it is. So look at opposing points of views. Do not look at just, say, imperative programming languages. Look at declarative programming. Look at, say, functional programming. Something like a Clojure or Scala can give you a lot more thoughts, right? Ideas than language like, say, Java or JavaScript or TypeScript or C, etc. Understand what monolithic architectures is before straight away plunging into microservices, where you have separate services running for each aspect or specific use case, right? Closer to the Unix philosophy. Try to work on web scale platforms. Try to work on much smaller projects like an IoT project where you're essentially working on an embedded platform with a lot of limitations. Work on diverse operating systems, especially if you're interested in system programming. And the most important thing is unlearning. Unless you are open to unlearn things which you have learned in the past, you will not be able to make progress, because you will find newer and newer things, and it is better not to be adamant that my way is the only way, right? Rather look at what you can learn from something new, how you can adopt it. And if that makes your road ahead simpler, I think that's the best way to take. Now, I would like to end with a quote from one of the leading experts on usability and design. It's a person called Edward Tufte, who would not definitely agree with the slide deck that I had presented. In fact, he has a very famous tirade against PowerPoints. Right? He says those are the worst ways to give a presentation. But he has written phenomenal stuff, done phenomenal research, right? Very well respected across the world. One thing he said about design, design isn't crafting a beautiful textured button with breathtaking animation. It's figuring out if there's a way to get rid of the button altogether. So this can be applied to software engineering also. When you're building something, rather than complicate it with a lot of moving parts, see if you can actually get rid of some of the moving parts, and that will yield much simpler solutions. So with that, I would like to take a pause. I hope I have been able to create some sparks of exploring simplicity further, right? Reading about, say, the design philosophies of Dieter Rams, Edward Tufte, the Unix philosophy, the industrial design principles of Lego, etc. Right? So thank you all. Thank to the CSC chapter for giving me this opportunity to talk about something which is close to my heart, which is to make things simpler while building products. Right? So I'll open the floor for questions.
Thank you, sir. Thank you very much for your wonderful presentation. Very clean and nice presentation, sir. So there are few questions which has been asked during the time of registration.
Sure.
I'll post one by one, sir. First question: is there any way to let AI dominate the software field in a different way, in which it does not affect any developer?
Okay, that is a tricky question. A good question nonetheless. And so we have, AI is not new, right? It's been around for decades, but we are seeing rapid advances and progress made in the last few years. And it is going to impact everyone. I don't think there is escaping it in any way. And it is impacting us in ways which we are not even realizing. Anything that you use today, your mobile phone, the applications that you use, everything has a piece of AI working behind the scenes. So it is going to continue. I would say that it will only accelerate till there are a set of regulations and compliance laws which come in from different countries and slow it down a bit. As a software professional or as a student, I think we need to embrace the advances in these technologies and be not afraid to learn or use any of those. Right? There are apprehensions whether this is going to take away a lot of jobs, etc. I don't feel that way at all. There will be a lot of optimization for tasks which are repetitive in nature, right? Where human intelligence is not required. Those areas you will find rapid adoption and huge amount of optimization also. But the fundamentals of computing and computer science are not going to change. Right? And for good software professionals, good academicians, the market is going to remain open for decades to come. So I don't feel it as a threat in any way. I hope I was able to cover at least part of that question.
Thank you, sir. Next question. Is ChatGPT really a threat to the software developers and IT industry?
Okay, I think I covered part of it earlier. So ChatGPT specifically is not a threat at all to IT developers. In fact, the whole area of large language models will help developers deliver faster, right, and with lesser bugs. So if you use something like Visual Studio Code for developing programs, right, you would have seen that there are plugins which help you do code completion, etc. GitHub has something called Code Pilot, which can help you write code by just writing comments or giving outlines of the code, etc. But then there are also examples of people asking ChatGPT to write a particular program, and it has written beautiful code sometimes, and sometimes it has written wrong code also. It's an iterative process. I think people who are adept at using the tools will get better, but people who are not clear about fundamentals are going to struggle with it. Going back to the building architecture analogy that I talked about earlier, all the electricians use the same set of tools, all the masons use the same set of tools, but still the quality and the output is not the same, right? That's the same thing that is with software engineering as well. Just because ChatGPT is there, not all the developers are going to become outstanding programmers.
Thank you, sir. Next question. How will it impact the society, more especially the unruly environments, without access to systems and equipments or tools for work and development?
Okay, I don't understand that question fully, but let me try to answer what I gather as the essence of the question. I think again it is with respect to the advances in AI, right? Where people who are going to use it for negative purposes, right, or malicious purpose, etc. So that is bound to happen. Uh, with every advancement in technology, it can be used in a positive way or a negative way, right? You have cloud computing, which is bringing very large amount of resources at your disposal with the click of a button. It can be used for good things or bad things. It's up to the end user to do that. But I think the positive overwhelmingly defeats the negative in such scenarios. And as practitioners, we need to look at only the positive aspects of it. There'll be some negative aspects to it as well, but those will be in the minority. And it'll get sorted out in over a period of time. There will be defense mechanisms, just like how evolutions happen.
Thank you
Yeah.
for that answer, sir. Final year student named as Vija has asked a question, that is, I'm a final year student, so how do I get practical experience of DevOps? And do you have any facilities for providing an industrial DevOps based project that we can get to work on as a final year project?
Okay. So DevOps, you can do a lot of hands-on examples, etc. So say most of the cloud platforms like Amazon, Google, Microsoft, etc., give you free credits to do pretty much any prototyping that you want to do on DevOps, right? So the will to learn is the only thing that is required, nothing else. There is enough material out there, very good material out there, so you can make use of it. On the second part of the question about internships or platforms, so we do have internships which we do every year. So we go to campuses as part of the campus placement program when students are in the 6th semester. For people or students who are selected, we give internship opportunity for the final year, 7th and 8th semester, where they can work with us, right? Part of that will be training. And once the training is done, they'll be working alongside our engineers on actual customer problems, solving customer problems, building world-class products. And the day they pass out of the college, the very next day, they join as a full-time employee or associate of matrimony.com. So we have been doing this for the last 2 years. And in fact, we also give pretty good stipend throughout the internship period also. So it helps us as well as the students in multiple ways, right? We are able to make sure that they are up to speed when they complete their curriculum, and they can also see how their theoretical learning can be used in a practical way. Now, if you are interested in pursuing something like this, so this is not specific to DevOps, but we do more on programming. The programming language does not matter, right? We do interviews in all programming languages. So if you are interested in any internship, right, then please feel free to drop me a mail. My mail ID is kiran.vijayakumar@matrimony.com, first name dot last name. And I'll forward it to the hiring team, which takes care of the internship and campus placements.
Thank you, sir. Next question. When blockchain application will reach layman?
Okay. Probably this, I'm the wrong person to be asked this question, because I have always been a big skeptic of blockchain or practical applications of blockchain, right? So I say this with utmost respect to the fundamental technology itself. In fact, the original paper on blockchain is a fantastic paper to read. It I would say it is one of the best papers to read among the academic papers published in the last couple of decades. But beyond certain use cases, I don't see this being adopted for a lot of use cases. In fact, for most of the use cases that blockchain practitioners talk about, they can be solved without using blockchain itself. So I would not keep waiting eagerly for blockchain to become available to laymen. If that was the case, we would have seen that already.
Thank you, sir. These were some of the questions. Now I request anyone of the participants, if you have some queries, you can just unmute yourself and ask Mr. Kiran, sir.
Somebody has raised the hand, Mr. Selvaraj.
Selvaraj from Coimbatore. Yeah. Selvaraj, you can.
Selvaraj?
Unmute and
Yeah, please go ahead. Selvaraj is not able to hear. Okay, I think Selvaraj has left the meeting.
Maybe he'll read that.
Anyone would like to raise your queries? Okay. Thank you, sir. Now I request our chair, CSI Chennai chapter chairperson, Ms. Mythili Prakash ma'am, propose the formal vote of thanks.
Thank you, Akila. Mr. Kiran, thank you so much, especially for your valuable time, busy working day, spending with us. Is really we blessed. We are very happy about it. Thank you so much. The session was quite interesting, and as you said, it is very simple to understand for any person, any level. Start with simple stories for easy understanding. So walk through that entire process right from designing till testing, and also about software engineering. It's very quite interesting. And thanks for our patient responses for the question and answer session also. Thank you so much. Thanks for the audience who have joined with us through this G-Meet and also through live streaming. Thanks for your interaction with your question and answer, which makes us more elaborate to understand and make it very useful. And also, thank you so much for the joining society, IEEE CS Madras and the ACM, and all the participants. Once again, the special thanks to Mr. PVS and Mr. HR Mohan, who is with us always to make so many programs. Thank you, sir. Thanks a lot.
Thank you all. It was my pleasure talking to all of you. Look forward to meeting again soon.
thank you. Thank you, Kiran.
Thank you, Mr. Kiran. Thank you.
Thank you.
Thank you, sir. Thank you, ma'am.
Rama ma'am, you can stop streaming.
Yeah, stop streaming and stop recording.
Recording, I'll stop, ma'am.
Okay, streaming also.
Today, next in the Monday meeting, the timing is at 4.